I'm Sverre. I'm here to teach you about the benefits of sub-1 GHz technology. Benefits including longer range, reduced power consumption, and better coexistence. Let's assume a simplified system where we have a transmitter and a receiver. The amount of power fed into the antenna is denoted PT. The distance is D, and the amount of energy received is PR. Simplified, PR, the received energy, is proportional to the transmitted power divided by the distance squared and the frequency squared. What's important is that the amount of received energy is greater than the chip sensitivity limit for the link to be operational. From this simplified relationship, we see that by keeping the power constant and the sensitivity constant, you get longer range simply by reducing the operating frequency. So, in the ideal world, these are the only parameters affecting range. In real life, however, there will be obstacles. There will be walls, there will be ceilings, even trees, humans. So, sub-1 GHz technology has better penetration capabilities than do, for instance, 2.4 GHz. And even more, sub-1 technology or waves are better at turning corners than higher frequencies. Meaning, using lower frequency, you get better indoor coverage. So, by looking at this simplified relationship, we see that increasing the distance D is possible by improving the sensitivity, a lower number. So let's have a look at a receiver. What are the building blocks? You have your LNA, you have your mixer, an ADC, and a filter. The channel filter has a finite bandwidth. It needs to be set according to your data rate, modulation format, and so on. And you also need to take into account any crystal inaccuracies. And the wider your bandwidth, the more noise into your channel, and the worse your sensitivity. So, just giving you a quick example. If you have a 10 ppm crystal and you operate at 900 megahertz, you could potentially get an offset of 9 kilohertz. So, ideally, that will be your transmitted signal. And if there's an offset between the receiver and the transmitter, you could potentially end up at 2 times 9 kilohertz, 10 ppm crystal, or it could be the other extreme, so it is. So your channel bandwidth needs to be at least as wide as this, okay? That's your signal bandwidth, and that's accounting for any crystal inaccuracies. Now, at 2.4, if you have the same crystal, 10 ppm, instead of these two, you will get your signal up here somewhere, and it's 2 times 24 kilohertz. And it will end up here, and your bandwidth needs to be at least as wide as this. Meaning you pick up more noise and you get degraded sensitivity and hence a shorter range. Range can also simply be increased by increasing the output power, but in doing so you will also consume a lot more current. So if you increase the operating frequency to 2.4 gigs, say, you will need higher output power, more current, and hence not a good fit for a battery-operated application. Alternatively, if you want the same coverage at 2.4 as you do at sub 1 gig, so that's your sub 1 gig link, you could potentially add a intermediate node which forwards information to the final destination. So that will do 2.4 gigahertz. Now, by introducing this additional node, you will increase the complexity as well as the system cost. And finally, we have coexistence. At 2.4 gigahertz, there are a lot of devices using different technologies such as Wi-Fi, Bluetooth, and BLE. The sub 1 gigahertz space is less crowded, and the likelihood of collisions is smaller, and there will be less retries in your application and hence reduced current consumption. To summarize, sub 1 gigahertz operation will give you longer range, reduced current consumption, potentially reduced cost, as well as better coexistence. Thank you for listening. If you need more information, please go to the TI website.